Hello everyone, my name is Dipen Chetri, BSc 3rd semester. Today I am going to discuss about operational amplifiers. So let's begin. So as its name suggests, this operational amplifier is basically amplifier, and the basic job of an amplifier is to amplify the input signal. Now let's understand why it is known as the operational amplifier. So in early days when digital computers were not evolved at the time, the different mathematical functions like addition, subtraction, integration, and depreciation were performed using these amplifiers. So just by connecting few resistor and capacitor, it is possible to perform the different mathematical operations, and that is why this amplifier known as the operational amplifier. So now if you see the circuit symbol of the operational amplifier, it can be represented by this symbol. So it consists of two inputs and one output. And most of the operational amplifier consist of two power supplies, the positive and the negative power supply, but there are many OPM ICs which runs on the single power supply. So now in this operational amplifier, the input terminal which is marked by the positive sign is known as the non-inverting input terminal, and another input terminal which is marked by this negative sign is known as the inverting input terminal. And it will get clear to you very shortly why it is known as the non-inverting as well as the inverting input terminals. So now if you use this operational amplifier, it is one kind of differential amplifier with the single output. It means that this amplifier amplifies the difference between the two input signals. So let's say V1 and V2 are the input signal which is being applied to this operational amplifier, and let's say the gain of this operational amplifier is A, then the output will be equal to A times the V1 minus V2. So let's say if we have applied a single input to this operational amplifier and we have grounded another input terminal, then at the output you will get A times V1, where A is the open loop gain of this operational amplifier. The reason it is being known as the open loop gain is that it is the gain of the operational amplifier when there is no feedback from the output to the input side. So suppose if you are applying the sinusoidal signal over here, then at the output that sinusoidal signal should be get multiplied by the factor of this gain, and at the output you should get the amplified sinusoidal signal. Now here the phase of this output voltage will be the same as the input voltage. Likewise, whenever we are applying input to this negative terminal and we are grounding another terminal, then the output of this amplifier will be equal to minus A times the B2, because the difference between these two input terminals will be equal to 0 minus B2, that is equal to minus of B2. So suppose let's say if we are applying the sinusoidal signal at the input, then at the output we will get the amplified sinusoidal signal which is having a 180 degree phase with respect to the input signal. That means the output will be get inverted by 180 degrees, and that is why this input terminal is known as the inverting terminal, because the output will be get inverted with respect to the input. So now here suppose if we apply the input signal between these two positive and the negative terminals, then at the output we will get A times this differential input signal, where here this A represents the open loop gain of this operational amplifier. Now this operational amplifier is a high gain amplifier, and the value of gain used to be in the range of 10 to the power 5 to the 10 to the power 6. So let's say even if we apply the 1 microvolt of a signal between these two terminals, and let's say if the gain of this OPM is 10 to the power 5, then at the output theoretically we should get 1 microvolt signal that is multiplied by the 10 to the power 5. That is equal to 100 volt. Or let's say if we apply 1 volt of a signal, then theoretically we should get the output as 10 to the power 5 volts. But that is not possible, and the output of this OPM is restricted by the biasing voltages that is being applied to this OPM. So the output voltage will be between these biasing voltages. So if you see the voltage transfer curve of OPM, then it will look like this. So here the x-axis represents the differential input that is applied to this operational amplifier, and the y-axis represents the output voltage of the amplifier. And here the slope basically represents the gain of amplifier which used to be in the range of 10 to the power 5 to the 10 to the power 6. Now here, let's say if the gain of OPM is 10 to the power 6 and let's say we are applying 1 microvolt of a signal. Then at the output we should get 1 volt of a signal. Likewise, let's say if we apply 10 microvolts of a signal, then at the output we will get 10 volt of output. But as we increase this input signal, then we will find that after some value of input signal, the output will get saturated to the value plus B set, which used to be less than the positive biasing supply. So in this way, as soon as the input voltage goes beyond some certain value, the output will be get saturated to the plus saturation voltage. And same is true for the negative input voltages. So as soon as the input voltage goes beyond some threshold value, at the output you will get minus saturation voltage. So whenever this operational amplifier is used in open loop configuration, that means there is no feedback from the output to the input side at the time. Even if we apply a small input signal between these two input terminals, then also you will find the output will be get saturated towards the positive or the negative biasing voltages. So this particular characteristic of the OPM is particularly useful when we use this OPM as a comparator. So this is one of the application in which this OPM can be used. But if you see this OPM can also be used in some any other applications, like in designing the active filters, oscillators, waveform converters, and analog to digital and digital to analog converters. Thank you.